Make me a host, ma'am. Good evening. A new chapter, polymers and polymerization. Last three small chapters we have, biomolecules and chemistry in everyday life. We'll finish that. Today, possibly the theory part of the polymers we will finish. Now, poly stands for many. Firstly, we'll understand like this. Mono stands for one. Mer stands for molecule. And poly stands for many. So, if we have only one molecule, it will be called as monomer. So, monomer means one molecule is called as monomer. Now, polymer means many molecules are called as polymers. So, these polymers are formed by the combination of many monomers. So if I take n numbers of monomers, if they combine, we get a polymer. So mono stands for one, poly stands for many, and mer stands for molecule. So when many molecules combine to give a polymer, this polymer will have very high molecular weight, and they'll have very high molecular weight. So polymer is defined as high molecular weight compounds formed by the combination of monomers. So when many number of monomers combine, 10,000 molecules combine to form a big molecule, a giant molecule with very high molecular mass, is called as a polymer. Now, the process in which polymer is prepared is called as polymerization. A process in which a polymer is prepared is called as polymerization. So there are different types of polymerization, different types of polymers, all that we're going to learn now. Now, polymer, firstly, what is the definition of a polymer? A polymer is defined as a high molecular mass, a giant molecule with very high molecular mass, formed by the combination of large number of one or more types of small molecular weights. When we say small molecular weights, they are nothing but monomers. So monomers can be of the same type, or it can be of the different type. That is why they say one or more type of small molecule called as monomers. The smallest units of which polymer is made is known as monomers. So the smallest unit in which the polymer is made is known as monomers. I told you mono stands for one and mer stands for molecule. The process in which a polymer is formed or prepared or manufactured is called as polymerization. Polymerization may be defined as chemical composition of number of similar or different molecules to form a single large molecule is called as polymerization. Now, a polymer in which is obtained from only one type of monomer molecules is known as homopolymer. Now, for an example, if we write like the CH2 double bond CH2, this is ethene. Now, this ethene, one more ethene molecule represent like this. These ethene molecules, when they combine, the pi bonds break, and we get a molecular chain like CH2, 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 2 molecules. If we take n molecules, so the chain length will keep on increasing. So these kind of polymers are called as homopolymers. They'll ask you an important, these are simple questions and an important question. What do you mean by homopolymer? Homo stands for same. A polymer formed by similar type of monomeric units are called as homopolymers. Example for homopolymer, polythene. This is polythene. So polyvinyl chloride is abbreviated as PVC. Polyacrylonitrile, PAN. Teflon is an example for a homopolymer. Guna rubber is an example for homopolymer. Now, the next one, if we have different types of monomeric units. Now, for an example, if we take a different type of monomeric unit, for an example, we have styrene, and we have 1,3-butadiene. So styrene is one monomeric unit. 1,3-butadiene is called as another monomeric unit. When these two monomeric units combine, they form styrene-butadiene rubber. The styrene-butadiene rubber is an example for heteropolymer. Or it is also called as copolymer, heteropolymer, or we can call this also as copolymer. In case of copolymer, the monomeric units are different. When monomeric units are different, they are called as heteropolymers or they're called as copolymers. So, example for copolymers or heteropolymers, it is Buna S rubber, butadiene styrene, nylon 6,6, hexamethylene diamine, and bakelite is also an example. So based on the monomer units, a polymer made by single monomer unit. Copolymer is a polymer made by different polymers. Kindly make me post. Thank you. So classification of polymers based upon their origin or based upon their source. So they are classified based upon their source as natural polymers, semi-synthetic polymers, or synthetic polymers. So natural polymers, polymers which exist in nature, they are called as natural polymers. Polymers which are found in plants and animals are called as natural polymers. These natural polymers are also called as biopolymers. So what is natural polymer? A polymer which are present or found in nature will be called as a natural polymer. These natural polymers are found in plants and animals. So natural polymers are also called as biopolymers. Example for natural polymers. Protein is an example for natural polymer. Polysaccharides, carbohydrates. Carbohydrates are example for natural polymer. Silk is an example for natural polymer. Wool is an example for natural polymer. Starch, cellulose, enzymes, natural polymer. So based on the source, polymers are classified into natural, semi-synthetic polymer as well as synthetic polymer. Now, the first one we learned, natural polymers. They can ask you, give an example for a natural polymer. So polymer which exist in nature, or which are natural in origin, which is found in plants and animals, are called as natural polymers. These natural polymers are also called as biopolymers. Now, semi-synthetic polymers. Semi stands for modification, partial. So semi-synthetic polymer, when we say chemically modified natural polymer is called as semi-synthetic polymer. When we say chemically modified natural polymer, now cellulose is a natural polymer. If you nitrate cellulose, we get nitrocellulose. So cellulose is modified with a nitro group. So therefore, it's an example for semi-synthetic polymer. Cellulose acetate. Cellulose is a natural polymer modified with acetate group, reacted with acetate group and modify the polymer. Then we get cellulose acetate. So chemically modified natural polymers are called as semi-synthetic polymers. Now, synthetic polymers. So synthetic polymers are also called as artificial polymers, polymers which are made in the industries or which are manufactured in the industries are called as synthetic polymers. Example for synthetic polymers, polythene, nylon, polyvinyl chloride, bakelite, dacron. All these are example for synthetic polymer. Synthetic polymer means polymers which are synthesized, which are manufactured, which are made. They are called as synthetic polymers. So this is the way polymers are classified based on their origin. That is one by natural, that's called as natural polymers. The second one is semi-synthetic polymers. The third is called as synthetic polymers. Next, classification based upon synthesis. When we say classification based upon synthesis, polymers are classified into two. One is addition polymerization polymers, the other one is condensation polymerization. Addition polymerization and condensation polymerization. In case of addition polymerization, the monomer units will get added on to each other without the elimination of any byproduct. There will not be elimination of any byproduct. So the monomeric units will add on to each other to form a polymer. Those are called as addition polymers. So addition polymers. Now, for an example, we learned this ethene. Again, we will try to learn. If you take two molecules of ethene like this, and if we heat it at required conditions, the pi bonds will break and these two carbon atoms will link. So therefore, we get CH2, single bond CH2, single bond CH2, and single bond CH2. A long chain we will get. We take N molecules of ethene. So this N molecules of ethene will give a polymer like this. This is called as polythene. So this polythene or polyethylene, now it is a product. There is no byproduct formed. So these kind of polymers are called as addition polymers. So addition polymers, these are polymers formed by addition together of the molecules of the monomers to form a large molecule without elimination of anything, without elimination of a byproduct. This process of formation of addition polymers are called as addition polymerization. Now, example, we have learned polythene. The second example is polyvinyl chloride. If we take polyvinyl chloride like this is vinyl group, vinyl chloride. This is not there. So another vinyl group, if we write like this, and at necessary conditions, when we heat, the pi bonds will break and we get CH2, single bond CH, Cl, single bond CH2, single bond CH-Cl. It goes on like this. It depends on the number of monomeric units. If we take n monomeric units, the chain length will keep on increasing. Here also, we can observe that there is no byproducts. Therefore, preparation of polyvinyl chloride is also an example for addition polymerization. Next is vinyl cyanide, or it's also called as acetonitrile. Acetonitrile. Now, not acetonitrile, this is vinyl cyanide, acrylonitrile. It's called as acrylonitrile. So vinyl nitride. So it is like similar example. It is CH2 double bond CHCN plus CH2 double bond CHCN. So when this is heated at a particular condition, the pi bonds will break and these carbon atoms will link. So we'll have CH2 single bond CHCN, single bond CH2, single bond CHCN. It goes on like this. So this is also, it's also commercially called as Orlon, polyacrylonitrile. It's also called as Orlon. You can see they are representing it by N units. So these are examples for addition polymerization. Now is isoprene. So isoprene is an example, is a monomeric unit in natural rubber. In natural rubber, we have, this is the IUPAC name for this molecule is 1, 2, 3, and 4. They can ask you what is the IUPAC name of the monomeric unit in natural rubber. At second position, we have methyl group. Therefore, it is 2-methyl 1,3 butadiene. So in natural rubber, the monomeric unit IUPAC name is 2-methyl 1,3 butadiene. So when this n number of isoprene units are polymerized, we get a natural rubber. So this is the partial structure of natural rubber. Here also we do not have a byproduct. Therefore, it is also an example for addition polymerization. Next here we have chloroprene. Chloroprene is an example for artificial rubber. Artificial rubber. So the monomeric unit in artificial rubber is chloroprene. So chloroprene units on polymerization, we get a neoprene rubber. Neoprene, it is an artificial rubber. This also is an example for addition polymerization. Next we have is styrene, benzene ring, and CH double bond CH2 group is called as styrene. And butadiene, 1,3 butadiene. So this is an heteropolymer. All the other polymers, what we were learning, they're all called as homopolymers. And here, what we're going to learn now is a copolymer. Instead of calling it as heteropolymer, we can call it as copolymer. In the NCERT, it is referred as copolymer. So styrene and butadiene, two different monomeric units. Therefore, it's called as copolymerization. When they are polymerized, we get styrene butadiene rubber. It's abbreviated as SBR. It is an example for a copolymer, and this also is an example for addition polymerization because we do not have any byproduct. Therefore, it is also an example for addition polymerization. The next, what we have, the next type of polymerization based on, excuse me, based on the method of synthesis. One is addition, the other one is condensation polymerization. Now, what is this condensation polymerization? Now, the condensation polymerization, the example is given here. Nylon 6,6. This is a 2-mark question. Now, what is the monomeric unit in nylon 6,6? One is called as adipic acid. Adipic acid, you have, it's an hexane 1,6 dioic acid. So first carbon, we have COH group, and the sixth carbon also we have COH group. And these two are linked with 4 CH2 group. This is adipic acid. The name of this is commonly called as adipic acid. Now, the next monomeric unit here is hexamethylene diamine. Hexamethylene diamine. Now, hexamethylene, 6 methylene groups, 6 CH2 groups, hexamethylene, 2 amine groups. Therefore, it's called as diamine. So, in case of nylon 6,6, the monomeric units are hexamethylene diamine and adipic acid. It is an example for copolymerization. So if n moles of hexamethylene diamine and n moles of adipic acid are heated at high pressure, what happens? One of the hydrogen and this OH group gets eliminated as water. Similarly, one of this hydrogen of the amine group and the OH group of this gets eliminated as water. So what happens? There is a bond formed between carbon and nitrogen. So the product what we get is, see, this OH gets eliminated. So we have written CO, CH2 4 times, CONH. So this is the bond. This is called as an amide bond. It is called as an amide bond. So CONH bond is called as an amide bond. And then we have C2H6 and we have NH, N times. This is called as nylon 6,6. Why it is called as nylon 6,6? Because the monomeric units, both the monomeric units have 6 carbons. Now here we have 4, 5 and 6 carbon. Here also you have 6 carbons. Since both the monomeric unit contains 6 carbons, it is an example for, it's called as nylon 6,6. And you can see there is an elimination of water. Since there is an, instead of writing minus 2 H2O here, we can write plus of n moles of H2O because we don't know how many molecules of adipic acid and how many molecules of hexamethylene diamine. Therefore, we write n mole. Since there is an elimination of byproducts like water here in this case, this is an example for condensation polymerization. Now, what is this condensation polymerization? Condensation polymerization are polymers formed by combination of monomers with the elimination of simple molecules such as water, alcohol, ammonia, HCl will be called as condensation polymers. So condensation polymers are also formed by the combination of monomers, but with the elimination of simple molecules such as water or alcohol. This process is called as condensation polymerization. Example, proteins are formed by condensation polymerization. Starch, cellulose, all these are examples for natural condensation polymers. And nylon 6,6 is an example for a synthetic condensation polymer. Polyester, terylene or dacron is an example for condensation polymers. We will learn about the polyester preparation in later stages. Now, we have learned 2 classifications. One is based on the source or based on the origin, and the next is based on their synthesis. Based on the synthesis, they're classified into addition polymerization and condensation polymerization. They can ask you, what is addition polymers? Give an example. So you should remember and tell addition polymers are polymers formed by the combination of monomeric units without the elimination of any byproducts. But in case of condensation polymers, it is a polymer, condensation polymer formed by the combination of monomers, but with the elimination of simple molecules like water, HCl, or alcohol, or ammonia also. And this process, and examples you should remember. Third, we have classification based on the mechanism. So polymers are also classified based on their mechanism. The first one is called as chain growth mechanism. So polymers can be prepared based on 2 mechanisms. One is called as chain growth mechanism. These polymers are formed by sucking chain. If I have 1 unit of CH2, double bond CH2 ethene, 1 more unit can be added here. So therefore, what happened? The pi bond breaks and we get CH2, this link. So 1 more unit can be added, like pi bond will break and you get CH2. Goes on. This process is called as a chain growth. The polymers are formed by successive addition of monomeric units to the growing chain, having a relative intermediate. This is followed by free radicals or carbocation or carb anion. So chain growth polymerization is an important reaction of alkenes and conjugated dienes. So polythene is a chain growth polymerization. Polypropylene is a chain growth polymerization. Teflon, polyvinyl chloride, polystyrene, all are examples for chain growth polymers. So the chain keep on getting increased. So the monomeric units goes on adding. therefore the chain length keeps on increasing. And it follows free radical mechanism. So chain growth of polymerization follows a free radical mechanism. Now, step growth polymerization. Next is step growth polymerization. These polymers are formed through a series of independent steps. Each step involves the condensation between two monomeric units, leading to the formation of smaller polymer like nylon, toluene, bakelite. See, stepwise. So one adipic acid plus one hexamethylene diamine forms one monomeric unit of nylon 6,6. Likewise, another adipic acid, another hexamethylene, another nylon 6,6, they combine. So therefore, it is a stepwise reaction. So these are polymers formed through a series of independent steps. Each steps involves the condensation between two monomers and leading to the formation of a smaller polymer. So 1 unit of adipic acid, 1 unit of hexamethylene diamine is a smaller polymer. So many number of smaller polymers will combine to give a larger polymer. This is called as a step growth polymers. Now, the next method of classification is based upon the structure. So based upon the structure, they are classified into linear polymer. We have three types of polymers. One is linear polymer. The next one is branched polymer. And the third one, what we have is called as a cross-linked polymer. Cross-linked polymer, or it's also called as three-dimensional polymer. Three-dimensional polymer. So based on the structure, polymers are classified into three. One is a linear polymer. The other one is a branched polymer. The third one is a cross-linked polymer. Now, when we talk about linear polymer, generally, if a polymer chain is like this, the hair, for example, if you take a hair, now this is different strands are like this. It's in the form, each are different. They do not have any connectivity between these two. So these are called as linear polymers. So linear polymers consist of long chain of atoms and are also called as one-dimensional polymer. So for an example, polythene is an example for linear polymer. Polyvinyl chloride is an example for linear polymer. Nylon and polyesters are examples for linear polymer. So linear polymer consists of extremely long chain of atoms and are also called one-dimensional polymers. The next is branched polymer. Now, when we say branched polymer, now if there is a branch like this, so this will be called as a branched polymer. So branched polymer will have, it's a linear polymer having branches, will be called as branched polymers. Now, the cross-linked polymers are three-dimensional polymer. Now, if we take this as an example, you can see there is an interaction. I'm showing an interaction between polymers, different polymers, different linear polymers. They are called as cross-linked, or they're called as three-dimensional polymers. Those polymers in which chains are cross-linked to give three-dimensional network and are called as three-dimensional polymers. Example for three-dimensional polymers. Bakelite is an example for three-dimensional polymers. We will learn what is bakelite, preparation of bakelite, all that in detail. Partial structure of bakelite, all that we're going to learn. Now, example for a branched polymer. Glycogen is an example for branched polymer. Low density polythene. Low density polythene is an example for a branched polymer. Amylopectin is an example for branched polymers. Now, the last classification we have is based on the molecular forces. Based on the molecular forces, polymers are classified into four. We're going to learn that in detail now. I'll erase this. Are you following?
Yes, sir.
Yeah. We'll try to finish this chapter today. Polymers, let's see. Now, based on the classification based on the molecular forces, they are classified as elastomers. Now, what are these elastomers? Polymers in which intermolecular forces between the chains are weakest, with few crosslinks that contribute elasticity or elastic property is called as elastomers. So polymers in which intermolecular forces are weak. So when they have weak intermolecular forces between the chains, they can be stretched. They can be stretched, and when we leave the when we remove the force, it can come back to its original position. Those are called as elastomers. So elastomers are elastic in nature. Why they're elastic in nature? Because the chains are held with, sorry, we can write just like this: chains are held with weak intermolecular force of attraction. Since the chains are held with weak intermolecular force of attraction, they have elastic character. Now, this elastomers, if it is heated with rubber, elastomers heated with sulfur, we get vulcanized, VULCAENIACD, vulcanized rubber. Vulcanized rubber, which is used in making tires, it has a high elastic property and wear and tear property. Therefore, it is used in the preparation or manufacturing of tires. So elastomers having very weak intermolecular force of attraction between the polymer chains are called as elastomers. They are elastic in character, and vulcanized rubber is an example for elastomer, very important example for elastomers. Next we have is fibers. Based on the molecular force, we have fibers. Fibers are thread-forming solids. Which possesses high tensile strength and high modulus. So fibers are polymers having a bit strong intermolecular forces, such as hydrogen bonding. You would have seen nylon ropes. You would have used nylon ropes. Even in the nylon ropes, you can see many strands are there, which are made as a thicker rope, and each strand do not have any connectivity with each other. So each strand will behave like a fiber. So nylon ropes is an example for the fibers. These are polymers which are a bit stronger in nylon 610 and terylene. Now we will learn about the preparation of nylon 66. Already I taught you how to prepare nylon 66. Now one more time I'm going to repeat because it is an important question. It is obtained by condensation polymerization of hexamethylene diamine 6 carbon and adipic acid. It's a dibasic acid having 6 carbon. 2 COH group we have, therefore it's a dibasic acid. Since we have 6 carbon atom, it's also called as nylon 66. Now this is adipic acid. This adipic acid, when heated with hexamethylene diamine, if it's heated with hexamethylene diamine, I told you the condensation reaction, this hydrogen and this OH gets eliminated, this hydrogen and this OH gets eliminated, and these CO and NH gets bonded. So we have CO here, this is a bond, you should show this bond because it is not satisfied with its valency, so therefore it's unstable. This bond has to be shown, CO and CH2 4 times, we have CONH, we have CH2 6 times, we have NH, and then this is called as nylon 66. So adipic acid and hexamethylene diamine, when heated at high pressure, we get nylon 66. Nylon 66 is an example for fibers. We have one more, nylon 610. So nylon 610 is obtained by condensation polymerization of hexamethylene diamine 6 carbon and C-basic acid. C-basic acid is 10 carbon atom like the COOH and CH2 8 times COOH. So this contains 10 carbon atoms, similar reaction as we learned with adipic acid. So it's an example for a fiber. Pterylene is also an example for fiber. Pterylene is otherwise called dacron, pteron, chronar, mylar. It is a polyester. See, here the linkage is amide linkage. Here the linkage is amide linkage. Here we're talking about a pterylene in which the bonding is polyester. The monomeric units are held together by a ester bond. Now, dimethyl terephthalate. Dimethyl terephthalate. Terephthalic acid. Now, this is benzene. If we have COH group here, the benzoic acid, you have one more COH group here. It is called as terephthalic acid. And if this hydrogen is replaced by CH3, this also is replaced by CH3, then it is called as dimethyl terephthalate. This dimethyl terephthalate, when allowed to react with ethylene glycol, this is ethylene. If the pi bond is removed, if the pi bond is removed, and in place of, to balance this valency, OH groups are added, this is called as ethylene glycol. It's called as ethylene glycol. So dimethyl terephthalate and ethylene glycol, or just it's called as glycol, are heated. We get diglycol terephthalate. What is this diglycol terephthalate? One of the hydrogen from here, and this OH gets eliminated as water. In place of the hydrogen, carbon gets bonded. Similarly, one of the hydrogen from here, and OH gets eliminated. So what's water? And this carbon gets bonded here. So that's the product we are getting here. This is called as diglycol terephthalate. And the byproduct, no, it's not so. So the whole CH3 group gets eliminated. CH3 group gets eliminated as CH3 and OH gets eliminated as methyl alcohol. Here also CH3 and OH gets eliminated as methyl alcohol. Therefore, we get diglycol terephthalate. This diglycol terephthalate will decompose to give pterylene. Third, based on the molecular force, it's important we should know that is called as thermoplastics and thermosetting plastics. Now, what is this thermoplastics? Now, a plastic which softens on heating and becomes hard on cooling, those are called as thermoplastics. These thermoplastics can be molded into different shapes because on heating it softens. We can mold it to a different shape and cool it, it becomes hard. This is called as thermoplastics. Polyethylene, polypropylene, polystyrene are examples for thermoplastics. Thermosetting plastics or resin. This thermosetting polymer becomes hard on heating and it cannot be remolded again. It is not capable of becoming soft on heating again. It becomes permanently hard. Therefore, it cannot be remolded again on heating. It doesn't become softened on heating. So those kind of polymers are called as thermosetting polymer. Example for thermosetting polymer is bakelite, aniline aldehyde resin, urea formaldehyde polymer. All these are examples for thermosetting plastic. What is thermoplastic? Thermosetting plastic, you should remember. Thermoplastic can be molded, remolded. On heating, it becomes soft. On cooling, it becomes hard. So it can be heated, remolded into different shape any number of times. Thermoplastic polymer, it's a polymer which becomes hard on heating and it becomes permanently hard on heating. And because of the extensive cross-linking, it gives a three-dimensional network and it cannot be recycled. This thermosetting plastic cannot be recycled. So that's called as bakelite. Bakelite switchboards you would have seen at home. Switchboards. These switchboards are bakelites. It's phenol formaldehyde polymer. We will learn about bakelites a little later. Now they can ask you difference between thermoplastic and thermosetting plastic for 2 marks. So you should remember thermoplastic softens and on heating and hardens on cooling. This process is reversible. Heat, it becomes soft, cool, it becomes hard. Again heat, soft, again cool, hard. So different shapes. Now thermosetting plastic becomes hard on heating, and the process is irreversible. Once it becomes hard on heating, it cannot be softened further. Therefore, it's irreversible process. Irreversible. Now, thermoplastic can be molded and remolded. This can be molded and remolded into different shapes. Here, it cannot be molded. It cannot be remolded or reshaped. This is thermoplastic is because of addition polymerization. And thermosetting plastic, it's because of condensation polymerization. Polymers, these are thermosetting plastics or polymers are formed by condensation polymerization. Thermoplastic, generally, they have linear structure. Thermosetting plastic, they have generally cross-linked. When we say cross-linked, enormous amount of bonding between the chain. Therefore, it cannot be remolded into different shapes. Now, monomers and polymers. It is only an information. Now, we're going to learn few reactions, which is required to be learned. Now, ethylene is a monomer. The polymer, what we get is polymerization. The type of reaction mechanism is addition polymerization. And this is also an example for homopolymers. Homopolymers. Now, propylene is a monomeric unit. You get polypropylene, and it is addition polymerization. And it's also an example for homopolymers. Now, vinyl chloride. Vinyl chloride is a monomeric unit. Polyvinyl chloride is a polymer. It is also a homopolymer, and it's a chain growth polymer. Chain growth polymer. Styrene, we get polystyrene. It's an addition homopolymer, linear chain polymer. Acrylonitrile. Acrylonitrile. CH2CHCN. CH2CHCl is vinyl chloride. This is acrylonitrile. So we get polyacrylonitrile, PAN. So acrylonitrile, when polymerized, we get polyacrylonitrile. It's otherwise called as OLON, and it is an addition homopolymer. Likewise, 1,3 butadiene, buna as rubber, addition polymerization. Vinyl acetate, polyvinyl acetate, addition homopolymer. This is CF2, double bond CF2. It is tetrafluoroethylene. This tetrafluoroethylene, when we polymerize, we get Teflon. We would have used Teflon tapes we would have used to prevent leakages, and Teflon non-stick cookwares. In modern day cooking, we use non-stick cookwares. So that is nothing but Teflon coated. Isoprene, natural rubber. Polymers, natural rubber. It's addition polymers. Likewise, chloroprene is a monomeric unit. Neoprene, it's called as artificial rubber. Again, addition homopolymers. So many polymers are there. This table you can just go through. We have to learn this. We have to remember this. All these four, what I've given, you should remember for our syllabus. Ethylene glycol and dimethyl terephthalate, you get terylene dacron. Their bonding is polyester. It's a copolymer because monomeric units are different. Step growth. Hexamethylene diamine and adipic acid, nylon. The type of bonding is polyamide. Copolymer, step growth. Phenol and formaldehyde and urea. Formaldehyde and urea is called urea formaldehyde resin. It's a copolymer, step growth. Phenol and formaldehyde. The polymer is named as bakelite. It's a copolymer because monomeric units are different. Step growth, thermosetting polymers. So we'll have to learn with the partial structure of bakelite, all that in the later stages. So now we will learn about some of the simple polymers which we have to learn. We have to learn with the mechanism of the polymerization. We will learn mechanism of polymerization a little later. This chapter, it's a small chapter wherein you will get 5 marks for a board exam. So this chapter, biomolecules, 5 marks. This chapter, 5 marks. Amines chapter, 5 marks. If you find organic chemistry a little difficult, kindly learn amines thoroughly, polymers thoroughly, and biomolecules thoroughly. So you should get 15 marks in the part D in your question paper. We will learn about some of the important questions here, what they can ask you. Preparation of polythene or manufacturing of polythene. Polythene, polyethylene, otherwise it is called as. So polythene, based on the this preparation follows free radical mechanism. Free radical mechanism. We will learn free radical mechanism possibly tomorrow, and then we'll finish up with the MCQs also. Now we will learn the preparation of polythene. So there are two types of polythene. One is called as low density polythene, polyethylene or polythene, low density polythene. So if we take a monomeric unit, ethene is a monomeric unit. If n moles of ethene we take, and if we heat this n moles of ethene at 350 to 570 Kelvin, 350 to 570 Kelvin at around 1000 to 2000 atmosphere. The pressure is very high. And in the presence of oxygen as a catalyst, in the presence of oxygen as a catalyst, we get a polymer, CH2, single bond, CH2, single bond, CH2, single bond, CH2, goes on like this. I told you how this length chain is formed. It's called as addition. Each unit, monomeric units, keeps on adding. It's called as a step growth, a chain growth polymerization. So this polymer has lower density. Therefore, it is abbreviated as LDPE, low density polythene. This low density polythene is used in making plastic packing bags, polythene bags you have heard, and it is used in insulation for electric wires and cables, and it's used in the manufacturing of squeeze bottles, toys, etc. Now, the next polymer we have is high density polythene. Now, this high density polythene is represented as HDPE, high density polythene. Now, what is this high density polythene? The reaction again, it is same. CH2 double bond CH2 N molecules. When we heat it at 330 to 340 Kelvin and 6 to 7 atmospheric pressure, in the presence of Ziegler-Natta catalyst. Ziegler-Natta catalyst, Z-I-E-G-L-A-R, Ziegler-Natta, N-A-T-T-A, Natta catalyst. They can ask you what is Ziegler-Natta catalyst. Now, conditions are different. You can see the conditions are different. Here, the monomeric units are same. For low density polyethylene, the temperature is very high, 350 to 570. Pressure is also very high, 1000 to 2000 atmospheres, and in the presence of oxygen. Here, in high density polyethylene, the reaction remains same. The product appears the same. But here, the condition is 330 to 340 Kelvin, and the pressure is very low pressure, 6 to 7 atmosphere, in the presence of the Ziegler-Natta catalyst. What is this Ziegler-Natta catalyst? Now, this is titanium, or maybe we can write like this, triethyl aluminium. C2H5 is aluminum group. C2H5 is ethyl group. Aluminum valency is 3. Therefore, triethyl aluminium and titanium tetrachloride is an example for Ziegler-Natta triethyl aluminium and titanium tetrachloride. And the solvent they use is heptane. Normal heptane is the solvent. So this high density polythene buckets, it is used in making dustbins. It is used in making housewares, pipes, bottles, toys, etc. So this is with respect to low density polyethylene and high density polyethylene. Remember, you write a statement. How low density polyethylene is prepared? It is manufactured by heating ethylene at 350 to 570 Kelvin at a pressure of 1000 to 2000 atmospheric pressure in the presence of oxygen or peroxide. We can use oxygen or we can also use peroxide as a catalyst. Peroxide as a catalyst. So we get low density polythene. This low density polythene is transparent polymer. It's a transparent polymer of moderate tensile strength, flexible and tough. High density polythene, high density polythene are tougher and they're harder and higher softening temperature. And they'll ask you difference between high density polythene and low density polythene. The next polymer which we are supposed to learn is, I will write it here, is polytetrafluoroethene. Polytetrafluoroethene. This polytetrafluoroethene is also called as Teflon. Polytetrafluoroethene is also called as Teflon. In preparation of polytetrafluoroethene, the monomeric unit is tetrafluoroethene. So ethene, we know it is CH2 double bond CH2. If these hydrogen atoms are replaced by F2, CF2 double bond CF2, this is tetrafluoroethene. This tetrafluoroethene, when it is heated with ammonium persulfate as a catalyst, NH4 twice S2O8, ammonium persulfate as a catalyst. When we heat it at high pressure, we get CF2 single bond CF2 single bond CF2 single bond CF2, goes on like this. This is called as polytetrafluoroethene, or it is called as Teflon. So it is the same, the molecule, the structure looks same as polythene, only in place of hydrogen it is CF2. What are the uses of this Teflon? Everybody knows that it is used in manufacturing non-stick cookwares. Teflon is made, used in making non-stick cookwares. It is also used in gaskets for cookers, gaskets, valves, oil seals, filter cloths, etc. So this is the other type of polymer which we are supposed to remember. Now, the next polymer is polyacrylonitrile. Looking for space. Polyacrylonitrile. This polyacrylonitrile is abbreviated as PAN. Now, polyacrylonitrile, it is acrylonitrile unit, CH2 double bond CH, CN. And if you take N molecules of this, and heat it in the presence of a peroxide catalyst, benzoyl peroxide will be using as a catalyst, or we can use hydrogen peroxide also as a catalyst. Any peroxide can be used as a catalyst. So what happens? The pi bonds will break. You will get CH2, single bond CHCN, single bond CH2, single bond CHCN. It goes on like this, the long chain. So since no space here, I've written here. This is called as polyacrylonitrile. This polyacrylonitrile is used in making carpets. It is used in making blankets, etc. This polynitro, it is used as a substitute for wools. It is used as a substitute for wool. So the next part of the topic is, I taught you the preparation of nylon 6. I've taught you. We have to learn one more preparation, that is nylon 6. We will learn the preparation of nylon 6 and possibly we can stop for today. So nylon 6, you can see it is not 6,6, it is nylon 6. So the monomeric unit in nylon 6 is caprolactam. Now this caprolactam, when heated with traces of water, we get, at high temperature, we get nylon 6. Now caprolactam, it is CH2 5 times, CH2 5 times, NH And you have a CONH bond, CONH bond. So I cannot write it like this, a cyclic molecule. So we should write it like this, CH2, 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 and we have C double bond O, and we have NH. This is the monomeric unit. This is caprolactam. When we heat this, what happens is we get nylon 6. The bond breaks here. When the bond breaks here, we have C double bond O. We have CH2 5 times. And we have NH. NH. Now, again, this NH will be bonded by another caprolactam unit, C double bond O, CH2 5 times, NH. Goes on. This is the structure of nylon 6. Nylon 6. They can ask you what's the monomeric unit in nylon 6. It is caprolactam. Caprolactam on heating with traces of water at high temperature, nylon 6 is formed. So we'll continue the class tomorrow. We'll learn with the preparation of polyesters and other part of the topic tomorrow. Thank you.